Alright, in this video we're going to talk about how to find a basis for the row space. Of a matrix. So last time we talked about how to find a basis for the column space of a matrix, and we did that in 2 steps. First we figured out what a basis for the column space is. If the matrix is in echelon form, you look at the pivot columns, and then we talked about how to deduce how to find a basis for any matrix using its echelon form. And for the row space it's similar, so let's just talk about what to do if the matrix is in echelon form. So if the matrix A is in echelon form, well, let's look at an example. So let's say that A is, well, I don't know, let's say it's this, okay? So I have 3 rows, this row, this row, this row. Now if you look at this first, so let's call this V1, V2, V3. So V1 is 1, 2, 0, V2 is 0, 0, 1, V3 is 0, 0, 0. Okay, well if you look at these, right, these 2 are obviously linearly independent, and this third one just doesn't contribute anything to the span, right? So the row space of A is the span of V1 and V2. Well, in general, by definition, it's the span of V1, V2, and V3. But V3 is a 0 row, so it's just the span of V1 and V2. And in general, when a matrix is in echelon form, the pivot rows, you can see, are going to be linearly independent. It's probably a good idea to do some examples to see why this is true. So the pivot rows are linearly independent. Now, if the matrix is in echelon form, right, every row is either a pivot row or a 0 row. So therefore, the pivot rows span the row space. So therefore, if a matrix is in echelon form, the basis is just a set of pivot rows. Okay, so make sure you understand this and also why it's true. Okay, so now let's talk about what happens if A is not in echelon form. Not in echelon form. Let's look at an example. So let's say A is that. Okay, so let's compare this to the echelon form. So the echelon form, okay, let's see what that is. Let's swap rows 2 and 3 and then multiply by -1. row 3 minus 2 row 2. I get the identity. Well, let's look at these 3 rows. So let's call this V1, V2, V3. Okay, so let's say V1 is this, V2 is that, V3 is that. I don't know. Now let's compare this with these three rows. Let's call this W1, W2, W3. Now notice that when you did the row reduction, right, what did we do? We did W2 is V2 minus V1, and W3 is V3 minus V1. So therefore, and W1 is just V1. So therefore, W1, W2, and W3 are in the span. They are in the row space of A, right? Because they're in the span of V1, V2, and V3. Conversely, okay, V1, V2, and V3 are in the span of W1, W2, W3. Okay, why is this? Because you can reverse. So we have V1 is W1, V2 is W2 plus V1, so that's W2 plus W1, and V3 is W3 plus V1, so it's W3 plus W1. And in general, this is true. So in general, row operations don't change the span of the rows. In other words, V1, V2, and V3 are going to span the same span as W1, W2, and W3. And that's because when you do a row operation, you're just replacing one row by a linear combination of the other rows. And each row operation is reversible. That's important. The fact that you can reverse these means that you can write V1, V2, and V3, the original vectors, as linear combinations of the rows of the new matrix. So this is a key fact. And so that means that the row reduction does not change the row space. Let's bold these, put them in a box. So that's a good thing. So to find the basis for the row space of A, just find the echelon form, right? The pivot rows of an echelon form.